Hi there, my name's Rob, and I'm an associate professor at La Trobe University, teaching robotics and electronics and engineering in general. And I've got with me Scott Carver. Do you want to introduce yourself, Scott?
Sure. Hi, everyone. I'm Scott Carver. I'm a disease ecologist and wildlife biologist at the University of Georgia, and yeah, work on wombats in Australia, among other organisms.
And one of the things that's actually brought us together is a robot that involves wombats. So, Scott, it was probably before COVID that we first started talking about this and implementing it. Do you want to tell us a bit about the idea and what you were trying to do?
Yeah, I mean, it's just such a fun story of I was giving a seminar at La Trobe University where Robert was and talking about my group's research at the time at the University of Tasmania, where we were working on wombats and a disease that impacts them called sarcoptic mange, and also just doing a whole lot of other research around trying to understand wombats in general and the challenges are that their burrows pose to doing research on them because they go hide down these burrows. And that after the seminar led to a conversation with Robert here and where we had a potential solution to that we could explore, which has been just a really fun opportunity to work together.
And flowing on from that, we published a paper together. UTAS put together a video that went viral. I think we've got 5.1 million views or something on it showing the inside of wombat burrows. I think people were just really excited to see what was going on there because people can't normally fit inside these things, can they?
No, no, exactly. They're once you become a grown up like us, we're definitely much too large to be able to crawl down a wombat burrow, and yet that underground world plays such an important role in the lives of these sorts of animals, and so trying to access that, understand more about them and challenges that they face was a really important aspect, and so trying to design something that could go down into that environment was really tricky and involved us basically working together and going through several design iterations to find something that could both like traverse that complex terrain yet be sort of compact enough to like squeeze down those sorts of environments.
Yeah, it's pretty tight, and there were like 90-degree turns that could happen, and steep ramps that go up and down, and it's all over the place. So, and I think we'll intersperse a few videos showing some of the views inside these wombat burrows to show some of the things we were dealing with in there. Maybe you could talk a bit about what you were trying to study inside these burrows, besides having a bit of a sticky beak and look-see inside them. What was the science behind it?
Wombats are really knocked around by this disease called sarcoptic mange, and this disease is caused by a little parasitic mite that basically digs into their skin and causes the disease, and it's ultimately deadly to them. And we know that wombats, they're relatively sort of solitary animals that don't come into a lot of direct contact with one another. But they down these burrows they move home from these burrows every sort of 1 to 9 days, 1 to 10 days. They will actually basically shift house, and so what we think is happening is that they did leave some of these mites down the burrows. The mites can survive for a period of time owing to the cooler temperatures and higher humidities, and then a wombat that's healthy can pick up some of the mites through that. So we think that's really important for the transmission of this, and so it was really valuable to have something that could help us gain access to that environment so that we could learn more about those environmental conditions that exist down burrows.
And I think we were dropping some sensors and things down burrows and retrieving those sensors and looking at environmental conditions there to see what sort of expected life cycle these mites would have inside these burrows.
Yeah, absolutely. So I mean, the main things we wanted to do was to look at sort of temperature and humidity and the burrows and compare that to what we understood from laboratory studies about survival of the mites, and then we could do this using these robots across multiple seasons of the year, and then actually develop a much deeper understanding. And one of the great outcomes was that we're able to sort of figure out that we think that the mites can survive down wombat burrows for about sort of 16 days during winter, we estimate, and about 5 or 6 days during summer, which is much less. And we didn't really know that the temperatures shifted so much seasonally down these burrows. We had a good feeling that they'd be quite stable on like a 24-hour cycle, but actually the research really helped us understand that they are really stable day to day, but season to season they actually change quite a lot.
So it sounds like it's bad news for mites in the summertime, but good news for them in the wintertime, and inversely for the wombats.
Yeah, exactly, and but that also helps us understand, why we sort of see some of the impacts that we do of this disease in wombat populations, and it's really helped grow our understanding of that, so that we can then better understand things about sort of the disease management and control in their sorts of populations as well.
Yeah, great. Well, maybe it's worth mentioning a few things about the robot itself, because that's kind of what captured a lot of people's imagination and has been really great to design. So small robot, we'll put some pictures up. It has a camera on the front, camera on the back, so you can see where you're going when you're reversing back out again. Has a little gripper there. That's not for pinching the wombat or anything like that. That's for retrieving sensors that we place down the burrow and that we can take back again. We could add extra things into it, and there's been discussions with other people that we might need to take some dirt samples and things for studying different disease characteristics there. We can log temperature and humidity directly on the robot itself. And for one of the iterations, we actually added a thermal camera there. So helps us spot the wombats a bit more easily because we can see their heat signature and we see something warms down there. We've got a few new iterations, and I'm working with a few different people now that are wanting to apply something like this to armadillos in South America. Someone's using one for foxes at the moment in Queensland. There's just been a lot of interest about studying these underground burrow sort of arenas that are just hard for us to access normally. So maybe I'll talk about a couple of the innovations that we're considering and might be on the cusp of implementing. One of them, the new version of the Wombat, we're moving away from having internal batteries within the WomBot, because once they go flat, you kind of have to wait a few hours to charge up. So the latest version I'm creating has a cordless drill battery that goes on the control center for it, so that when it goes flat, you just pull that one out, plug a new one in, and you can keep on driving for a few hours. So that speed things up a bit. And one of the other things that we're looking at doing is putting a LiDAR on the WomBot, so that we can kind of take a cross-sectional area of the burrow and hopefully reconstruct them later on and be able to see what the burrow actually looks like. The final thing, and this kind of came of necessity, not of want, that the people that were manufacturing the rubber tracks that we're using went out of business. I was importing them from the US, and they just don't seem to make them anymore. So we've actually created some new 3D printed tracks made out of plastic. It's PETG plastic, but it also means that we can have any geometry of tracks that we want. So we can make them steeper or narrower. These ones, we put extra treads in them, so they're less likely to slip as they're traversing around. And it also means that if one of them breaks or something like that, we can just 3D print the new part and put a new one in. So there are a few of the kind of innovations that we're looking at, trying to make it a bit more user-friendly and a bit more applicable in different environments. I'm not sure if there's anything else that jumps to mind, Scott, that would be good to see in some new WomBots into the future, or new things you'd like to study in this sort of area?
Yeah, I think there's actually a lot of demand for these sorts of products and research. There's lots of different animals that actually like dig burrows underground, and inherently they're just sort of hard to sort of study. And innovations in technology like these just really help open up new doors that sort of haven't been available to biologists like myself. To be able to study those. And I remember during our early design iterations, we were trying to, the kind of the key challenges were that it was like, we had like rough terrain, so you had to have something that had like lots of grip but could clear the ground, and like sort of undulations in that, but yet it couldn't be too high and it couldn't be too wide. And so it sort of like really creates these sort of design constraints that I think Robert, you've been really great at sort of trying to solve those sorts of puzzles along the way. And you know, since we've done that work, I've also been using it to try and like look at things like gopher tortoises here in the southeastern US, which are also, you know, a tortoise that digs burrows, and that lots of other animals use as well. So that has like, ecologically very important roles in the environment, and so it presents sort of similar challenges. They're a bit flatter, so you kind of can't have your robot be quite as tall and that sort of thing. So again, a design constraint, and I think, you know, some of the other animals that you've subsequently ended up working on have meant that you've had to sort of like adapt the design for kind of the biology of those sorts of animals to address the different kinds of environments that they are. So I think this is sort of a really interesting technology, and naturally has generated a lot of interest just because of the kind of uniqueness of those environments and the challenges of working with organisms.
Yeah, thanks for that, Scott. It was some of those constraints you were talking about, basically on the size of the burrows, that was one of the reasons we were taking these batteries out. I think the original Wombat had 3 of these lithium batteries in there, and opted for a battery like this that was external at the user end. We were able to shrink things a centimeter in one direction and a centimeter in another direction, and that's really helped miniaturize things a bit. What I'll do is include our contact details at the end of this video. So if you're interested in this further or want to get in touch, please do so. It's been great talking to you, Scott, and finding out a bit about the journey of the WomBot and where it's been used and how it's being used.
Yeah, it's great to talk to you, Robert, as well. And yeah, I really love the innovation that you've brought to this area of research. It's been such a game changer for us biologists.
Brilliant. Thanks again.
Thank you.